Hi, my name is Sue Borchert. I'm a PhD candidate at the University of Wisconsin-Milwaukee in the Geography Department. My poster is titled Simulated Effects of Climate Change and Withdrawals from High-Capacity Wells on the Streamflow and Groundwater Elevations in northeastern Wisconsin. The study area is the Wolf River Basin. The basin is an example of the varied geology and land uses found within the state of Wisconsin, and it spans parts of several counties: Forest, Langlade, and Oneida. This study attempted to demonstrate the simultaneous effects of climate change and groundwater withdrawal from high-capacity wells on the hydrological system within the study area. In Wisconsin, the number of high-capacity wells has increased substantially, and concerns have been raised about their impact on both groundwater levels and stream flow. At the same time, Wisconsin's climate has been changing, with both annual precipitation and average temperature trending upward. To simulate how both climate and withdrawal rate will affect Wisconsin's water resources, two models were incorporated. SWOT, the Soil and Water Assessment Tool, was used to simulate the change in the recharge rate, and then ModFlow from the USGS was used to simulate the change in hydraulic head. Both models were run 4 times, starting with the SWOT model. The first run used the current climate conditions. The second SWOT run used the future predicted seasonal precipitation values only. The third run used both the predicted seasonal values for precipitation and temperature. The values were from RCP 4.5 model. The fourth run again used the future predicted seasonal values, but from RCP 8.5. Both RCP 4.5 and RCP 8.5 are both estimates of future climate from the Wisconsin Initiative on Climate Change Impacts. The RCP 4.5 scenario assumes that some measures are taken to reduce emissions and conserve forest land to store carbon, while the RCP 8.5 model assumes very high carbon levels and is the most extreme scenario. The SWOT models predicted that future increases in Wisconsin's annual precipitation would cause increases in groundwater recharge of 11%. and streamflow increases of 14%. But the future increases in temperature will leave the state with a net deficit of 23% in streamflow and 20% in groundwater recharge. These predicted recharge rates from the SWOT model were then used as input for the 4 ModFlow models. The first ModFlow model was run using the current recharge rate and also used the current high-capacity well withdrawal rates. The second model again used the current withdrawal rates, but used recharge rates from the third SWOT model. Model 3 was chosen because the RCP 4.5 scenario was assumed to be more accurate due to the downscaling performed for the state. The third model used the same recharge rates as Model 2, but with the withdrawal rate was increased threefold to simulate the withdrawal rate increase seen over the last 3 decades. The fourth model used the same recharge rates as Model 2 and 3, and the same increased withdrawal rate as Model 3, but the 3 high-capacity wells with the highest withdrawal rate were closed. These are the results. By subtracting ModFlow Model 1 from Model 2, we find that the mean decline in hydraulic head that was contributed to a change in climate over 5.5 decades was approximately 2.9 meters. By subtracting ModFlow Model 2 from Model 3, we find that the mean additional change in hydraulic head that was contributed to the potential threefold increase in the withdrawal rate was an increase of approximately 0.4 meters, but this was averaged across the entire study area. Significant declines in hydraulic head were seen in areas near clusters of high-capacity wells, specifically in an area called the Anagle Flats in the southeast portion of the study area. By subtracting ModFlow Model 2 from Model 4, we find the same increases in hydraulic head as in the prior model. However, the maximum declines were mitigated from approximately 43.3 meters to approximately 42.8 meters, a difference of 0.5 meters. And the declines around the cluster of wells in the southeastern portion of the study area were significantly mitigated. In conclusion, this research yielded knowledge of the role of simultaneous hydraulic stresses, both natural and anthropogenic, on both stream flow and hydraulic head. More specifically, the study showed that predicted increases in temperature due to climate change over the next several decades will lead to decreases in the available fresh water. These decreases to both groundwater and surface water are despite the predicted increase in precipitation. Further losses in the resource will be expected if the growth in the use of high-capacity wells continues at its current growth rate. The study also found that substantial savings of this resource can be managed by selectively reducing the number of wells allowed to operate. This study highlights how rising temperatures, along with an increased use of groundwater for agricultural irrigation, could decrease Wisconsin's available groundwater resources despite the predicted increase in annual precipitation over the next several decades. Thank you.